Alright, so in this section we're going to talk about radians and degree math. Let's first talk about parts of an angle. A ray is a part of a line that has only one endpoint and extends forever in the opposite direction. An angle is formed by two rays that have a common endpoint. So here are my two rays, and the common endpoint here is the vertex. One ray is called the initial side, and the other ray is called the terminal side. A rotating ray is often a useful way to think about angles. The endpoint of an angle's initial side and terminal side is the vertex of an angle. And something that you should be mindful of is an angle's in standard position if its vertex is at the origin and the initial side is on the positive x-axis. So here's a diagram of that. So here's our coordinate plane, x, y. Let's put our vertex at the origin. My initial side is on the positive x-axis. My terminal side can be in any quadrant I want it to be. Wherever the terminal side ends, let's call this alpha, we consider that angle to be in that quadrant. So this angle is in quadrant 3. Let's draw another diagram. This angle is in quadrant 1. This angle is in quadrant 2. And this angle is in quadrant 4. So let's call this theta, beta, and let's call this one alpha 2. So depending on which quadrant the terminal side is on is what we classify that angle in being in that particular quadrant. If the initial side and the terminal side, let's say that that's where that angle extends to, lies exactly on the x or the y-axis, we call that a quadrantal angle. So it's in a specific quadrant, it's on an axis. Alright, positive angles are generated by counterclockwise rotations. Thus, let's call this alpha, is considered a positive angle. Negative angles are generated by clockwise rotation, so let's call this one theta. So you can see clearly in this diagram that theta is going clockwise. It's considered a negative rotation. An angle is called, again, quadrantal angle if its terminal side lies on the x or y axis. If a standard angle has a terminal side that lies in the quadrant, then we say that the angle lies in that specific quadrant. So this one we would say that the angle's in quadrant 2, and this one we would say that the angle's in quadrant 4. Also remember definitions for angles. This is considered acute because it's less than 90. This is considered a right angle. This is considered an obtuse angle because it's greater than 90 degrees. And then we also have straight angles that are exactly 180 degrees. Let's define what a radian measure is. Think about radians and degrees like different forms of measurement for an angle, like Celsius and Fahrenheit. We measure temperature with that, different measurements, but we're measuring the same thing. So same concept here, and where does that definition come from? 1 radian is the measure of the central angle, so here's our central angle here, of a circle that intercepts an arc equal in length to the radius of the circle. So here you can see how it's remaining equal in length. Whether I have the arc is 3 times r, twice r, once r, that's where that definition is coming from. And we can obtain radian measures using this definition as well. And this is specifically in radian measures. We will end up in radian measures if we take our arc length s and divide it by r, or radius. When we talk about angles formed by rotations on terminal sides, let's start exploring this a little bit. Okay, I know if I go around a circle, one rotation around a circle, that's considered 360 degrees. In terms of radians, we say that that's 2 pi radians. We know that half a rotation around a circle, let's take a look at my diagram here, that's 180 degrees. In terms of radians, that's pi radians. So pi radians is equivalent to 180 degrees. Now notice that I took half of 2 pi to obtain pi. I could take half now of pi and end up with 90 degrees. So this measurement I know corresponds to 90 degrees. So half, or pi over 2 radians, just like I said, I'm going to take pi, which is 180 divided by 2, and that's where this is coming from, that's equivalent to 90 degrees. And then we could take that even further and think about taking 3/4 of 360 degrees. Okay, 3/4 of 360, remember 2 pi is equivalent to 360, that's going to be 3/2, okay, or 270 degrees. Okay, I can even further divide my coordinate plane into parts of 8. Let's take a look at that. Okay, so here's our x-axis, here's our y-axis. Before I start rotating, I start with 0 radians or 0 degrees. We established that this is 90 degrees or pi over 2. We established that this is pi or 180 degrees. We established that this was 3 pi over 2 or 270 degrees. So keep that in mind. And now I'm going to take my coordinate plane and I'm going to actually break it up into 4 parts. Okay? At the top and 4 parts at the bottom. So quarters. So here would be, and think in terms of radians, pi over 4. Or 1/4 of 360 degrees, which is 45 degrees. Add another 1/4, we're going to get 2 pi over 4, which we established was pi over 2. Add another 1/4, we're going to get 3 pi over 4. Add another 1/4, we're going to get 4 pi over 4, which is equivalent to pi. Add another 1/4, we're going to get 5 pi over 4. Add another 1/4, we're going to get 6 pi over 4, which is 3/2. Add another 1/4, 7 pi over 4. Add another 1/4, and we're going to get 8 pi over 4, which is equivalent to 1 rotation, 360 degrees, or 2 pi. And this is a good trick to remember when we're going to be doing concepts with the unit circle. So come back to this diagram to help you in the future. Alright, this example says to draw and label each angle in standard position. So here I have alpha, beta, theta. Think of those like the names of those angles. So we want to graph alpha in standard position. Remember, that means that the initial side is going to be on the positive x-axis. The terminal side can be wherever. So here's x, here's y. Here's my initial side. 3 pi over 2, we kind of just explore that on the diagram. I know that 2 pi over 2 is going to be pi, so I must be greater than here. And then I have an additional half, which is equivalent to right here. So here's me extending alpha equals 3 pi over 2. Now we're going to draw beta. Beta is 2 pi. We know that that's 360 degrees. So let's put that in standard position. Here's x, here's y. Here's my initial side, but we're coming right back to our initial side. So here's beta equaling 2 pi. Now we have 7 pi over 4. That's almost to 8 pi over 4, and we know that 8 pi over 4 is equivalent to 2 pi. So 7 pi over 4 is just shy of that, and if we think back to the diagram that we just did, 7 pi over 4 was in here. So my angle is extending to here. So here's 7 pi over 4, and this is theta. Coterminal angles are angles that have the same initial side, the same terminal side, but different degree measurements. Let me show you a bunch of examples. Okay, so here's our coordinate plane. Let's take pi over 4 because we already established where that was. So here, let's call this theta equals pi over 4. Okay. In order to obtain the same initial side, I'm going to start at the same positive x-axis, but in the same terminal side but different degree measurements, I could just start rotating in a circle. Now I have 360 plus pi over 4, or 2 pi plus pi over 4. So let's call that beta in blue. So 2 pi, which is equivalent, remember, to 8 pi over 4 plus pi over 4, we're going to end up with 9 pi over 4. Now if I'm going in the opposite direction, I can also create a negative rotation. So let's take a look over here and notice that I have the same initial side and same terminal side but different degree measurements. So now in order to obtain that negative angle, I just take pi over 4, and I subtract 2 pi. Remember, we established that 2 pi is 8 pi over 4. And we end up with negative 7 pi over 4. And negative 7 pi over 4 lies in quadrant 1. Pi over 4 lies in quadrant 1. And so does 9 pi over 4. Why? Because they're coterminal angles. They have the same initial side, same terminal side. So in order to find coterminal angles, we can just keep adding 2 pi, subtracting 2 pi. If we're in degree measurements, we're going to add and subtract 360. And however many cycles it is that we're looking for. So let's take a look at an example. Alright, so let's find 2 positive and let's say 2 negative angles that are coterminal to the given angle. So let's take negative 3 pi over 4. It might help to draw a picture. So let's put that in standard position. Here's our x-axis, here's our y-axis. Our initial side starts here, and we extend it 3/4 is almost to 4 over 4, which again would be pi, but we're going in negative rotation, so that's going to be negative pi. This is going to be negative pi over 2. So this would be negative 3 pi over 4, and let's call that theta. So if I'm looking for the positive angle that has the same initial side, same terminal side, and I'm looking for that angle, I could go back to the diagram that I drew before, but let's do it algebraically. Let's add 2 pi. And remember, 2 pi we established is equivalent to 8 pi over 4. So we're adding 8 pi over 4, and we're going to end up with 5 pi over 4. If I want to find another positive angle, which the instruction said to do so, I want to add another 8 pi over 4. So 5 plus 8 is going to be 13. So the two positive coterminal angles are 5 pi over 4 and 13 pi over 4. In order to find the negative one, I need to extend the rotation 360 degrees, including that given angle. So I'm going to take negative 3 pi over 4 and subtract 2 pi, which we said was 8 pi over 4. And that is going to give us negative 11 pi over 4. If I want another negative rotation, I just keep subtracting 2 pi, which is minus another 8 pi. So that's going to give us negative 19 pi over 4. So our 4 solutions are negative 19 pi over 4, negative 11 pi over 4, 5 pi over 4, and 13 pi over 4. Now we're going to do 5 pi over 6. Let's draw a diagram, and remember 5 pi over 6, 5/6 is greater than a half, and I know a half exists over here in the positive y-axis. And it's almost 2 pi, and remember pi is over here. If it helps you always label your coordinate plane, you know here's pi over 2, pi, 3 pi over 2, 0, and 2 pi. So that way when you're filling in where that angle goes, you can have a better estimate. So I know that it must be around here, and that's what I'm looking for. So this is, let's call this theta equals 5 pi over 6. It's in standard position, and I want to find a positive and a negative coterminal angle. Same initial side, same terminal side, different degree measurement. So the negative one would extend in this direction, same initial, same terminal. Let's call this alpha. So if I'm looking for alpha, I'm going to subtract 2 pi. Common denominator, rewrite it, multiply this by 6 over 6. That's going to give me 12 over 6. So 5 minus 12 is negative 7 pi over 6. And in order to find another negative rotation, you would just subtract another 12. So that would be negative 19 pi over 6. So that would be our two negative rotations. Now let's say we're looking for the positive angle measurement. So remember, that's going to be theta. Theta is our blue angle, or given. And we're going to take the degree measurement, extend it one time, same initial side, same terminal side, but now we have just an increase in 360, which is an equivalent to 2 pi. And remember, we established that that's equivalent to 12 pi over 6, which is 2 pi, and 12 plus 5 is 17. Add another 12 to that, and you get 29 pi over 6. So your two positive rotations are here. Alright, so complement and supplement. Complementary angles sum to 90 degrees. And in order to find the angle's complement, you're going to take pi over 2 minus 90, or 90 minus whatever that angle measurement is. In order to find the supplementary angles, remember that they sum to 180 degrees, and remember that's equivalent to 180, so I can also do 180 minus whatever that angle is. or pi minus the angle. Both complements and supplements should be positive angles. Alright, so here's an example. It says, if possible, find the complement in the supplement. Well, 3/4 is greater than a half, so it has no complement. But it does have a supplement. And remember, we're going to take pi. We might get a minus 3 pi over 4. Common denominator changes that to 4 over 4, and your answer is pi over 4. Let's take a look at B. 5 over 6, that's greater than a half. So it does not have a complement, it does have a supplement. So I'm going to do the same thing. Subtract it from pi. Common denominator would make it 6 over 6, and your answer is pi over 6. Here's a good diagram to include in your notes. Whether we have it in radians and degree conversions, this is what it looks like. This is called a unit circle. And here again we can break up our coordinate plane. Remember, I taught you to break it up into pieces of 8. We can also break it up into pieces of 12. Ignore the pi over 4, start at pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 7 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, and then etc. and continue it on all the way around the circle. Okay, over here we have our negative rotations, and notice where they're lined up. In the negative rotation, everything's consistent. Here's negative 30, negative 45, negative 60, negative 90, etc., extending 360 degrees in the negative rotation. Right, when converting back and forth from angles to radians or degrees to radians or radians to degrees, you want to use this conversion. And I don't necessarily memorize it like this. I just think of it as dimensional analysis, and whatever I want to reduce, that has to be diagonal. So if my pi is here, I need to have it diagonal, so my pi is an example. Okay, convert the angle from radians to degrees or vice versa. So I'm trying to reduce degrees, so that has to be diagonal. Radians at the top. Okay, 0 reduces, and 3 goes into 18 6 times, so that's pi over 6. Let's take a look at 160. I need my angles, my degrees to reduce, so that goes diagonal to that. That reduces, and 16 over 18 reduces as well to 8 pi over 9. 8 pi over 9. If we're converting pi over 2, remember you want the pi's to be diagonal, so they reduce. So now it's flipped, it's reversed. The pi's reduced, 2 goes into 180 degrees 90 times. 3 pi over 4, again, you want the pi's diagonal to that. Now you want to reduce this. The pi's reduce, and 4 goes into 180, 45 times. 45 times 3 is 135 degrees. Alright, let's switch the topic a little bit. Remember that S equals R theta can be manipulated. I presented that to you in the beginning of the presentation. And S represents our arc length, R is our radius, and theta is our central angle, and it must be expressed in terms of radians. For the area of a sector, that would be area of this shaded region, and that formula would be A equals half R squared theta. R is the radius, theta is the central angle, it must be in radians. We can use that to find the length of the arc, the area of the sector for this given information. So let's take a look at this first part. So if I'm looking for S equals R theta to answer the first question, that's part A, I'm just going to substitute. S equals 3 times 120. However, remember this has to be in radians, so let's convert it. 120 times pi over 180. This reduces. 12 over 18 reduces as well to 2 pi over 3. So that gets substituted in here. Here, the 3's reduced. Let's leave our answer in terms of radians. We don't know the measurement, so we're just going to write 2 pi units. For part B, we're looking for area of the sector. Area equals half R squared theta. So here we're going to substitute half. R is 3 squared. Theta is 2 pi over 3. So let's go ahead and simplify that. So that becomes half times 9 times 2 pi over 3. And here I'm going to reduce. I'm not going to multiply across. So that goes in there 1 time. That goes in there 3 times. So your answer is 3 pi units squared, because we're talking about area. Alright, obviously not drawn to scale. We want to go ahead and we want to find the arc length, our S equals our theta, so let's substitute. This is already in terms of radians, so we're good. We just need to substitute. S equals 4 pi over 5 times 7 in centimeters, so now this time we have our unit of measurements. So all we have to do is multiply. S equals 7 times 4, which is 28 pi over 5 centimeters. Now we want to find our area, so that's part B. Remember, area equals half r squared theta. So let's start substituting. Half, r was 7, and theta was 4 pi over 5. So that's half of 49 times 4 pi over 5. I'm going to do what I did before. 2 goes in here once, goes in here 2 times, so 49 times 2, 98 pi over 5 units squared. Alright, let's take a look at this last example. We want to find theta in degrees and radians with the given information. Here we're given the arc length. Remember, that's S. And we're given r is equal to 3. So here I can manipulate my formula. S equals r theta. So let's start substituting. So pi equals r theta. Now I just have to divide both sides by 3. And I get pi over 3. I want to convert it, so I'm going to multiply pi over 3 times 180 over pi. This goes in here 60 times. That reduces, so that's equivalent to 60 degrees. Alright, this time we're given area of sector, and remember we're looking for theta. So I'm going to manipulate this formula this time. Half r squared theta. So 24 pi equals 1/2 6 squared theta. So that's 24 pi, 6 squared is 36, half of that is 18 theta. Divide both sides by 18, and now we're going to reduce this. And our answer is, they're both divisible by 6, so our answer is 4 pi over 3. And I want to convert that to degrees now, so I'm going to take theta, 4 pi over 3, multiply it by 180 over pi. This reduces, 3 goes in here 60 times, and 60 times 4 is 240 degrees.